Here we have an example of repeated roots where we have a repeated root of 3, and here we're going to use partial fraction expansion as well as the translation property to find the inverse Laplace transform for this function here. So first, with repeated roots, we'll expand this using partial fraction expansion. 2s plus 5 all over s plus 3 squared, where we can break this up into a over s, let me make that minus, s minus 3, so we have a s minus 3 here, plus b all over s minus 3 squared. Now the numerator, what will yield is 2s minus 5 is equal to a s minus 3 plus b. Multiplying it out, we have as minus 3a plus b. Comparing coefficients of 2s and as implies that a is equal to 2, and then when I substitute 2 into minus 3a plus b, setting the coefficients equal to minus 5, we have that implied as minus 3 times 2 plus b is equal to 5, which means that b is equal to 11. So now we'll substitute those coefficients into this expression now, our expansion of a, where a is now 2, so it's 2 over s minus 3 plus 11 over s minus 3 squared. Using linearity, it's the Laplace transform in the individual terms here, 2 over s minus 3 and plus the inverse Laplace transform of 11 over s minus 3 squared. Well, we note that the inverse Laplace of this guy is just 2e to the 3t, and for this second one, since it's like 1 over s squared with a translation, so this is just plus 11 t e to the 3t, and that's the inverse Laplace transform is given. So here's another example associated with repeated roots, and we're going to solve this problem using the idea of modifying the function here so that we can recognize and put it in the proper form to find the inverse Laplace transform. So what we have here, we note that s squared plus 4s plus 6 has no real zeros, so there are no linear factors. So we need to complete the square in the denominator. So s divided by 2 plus 5 over 3 all over s squared plus 4s plus 4 plus 2, where we broke up the 6 into 4, 2, so we can complete the square here. So that's s over 2 plus 5 thirds all over s plus 2 squared plus 2. Well, we recognize that it's either the sine and cosine functions at the denominator right here with a translation property of e to the minus 2t. So we have to put it in that form. So we note that s minus 2 in the denominator plus 5 thirds, in order to have that s plus 2 form, can be rewritten as 1/2 s plus 2. Well, here we have 5 thirds right here, so in order to put s plus 2 here, we have 1/2 s, that's here, and then 1/2 plus 2 is 1, so we need to subtract 1. So we'll subtract 3 over 3 in the numerator, and we have s plus 2 squared plus 2. Well, this equals to 1/2 s plus 2 all over s plus 2 squared plus, and we'll put it in the form of either the sine or cosine of square root of 2 squared. So that's plus 2/3. 2/3 came from 5/3 minus 3 over 3, and that's s plus 2 squared plus square root of 2 squared. So in order to put this in the proper form, we multiply by square root of 2 and we divide by square root of 2, so we don't change the overall function. But now we have this constant term in front of our cosine. So now we can rewrite this in here as the inverse Laplace transform now for this expression, s over s plus 2. This is now in the proper form, s plus 2 squared plus square root of 2 squared, and this is the Laplace transform again for this term, and we're using linear property, so we're treating each term separately. Inverse Laplace transform of 2/3 divided by the square root of 2, and then we recognize this form now to be the sine term. So it should be recognized that this has a translation property and this has a translation property. So the resulting factor here would be just 1/2 e to the minus 2t cosine of square root of 2t. And the second expression here would be, simplifying, here the 2's cancel, that leaves square root of t in the numerator, 3 at the denominator, and so this would be sine e to the minus 2t sine of square root of 2t. So that's our result for finding the inverse Laplace transform for this expression here, and this is our corresponding, we'll call it f of t. So here is our inverse Laplace transform for this function right here.